This is just an outline. We just had to switch to the PDF, so hopefully it's not, the formatting will still be consistent. But forgive me in advance if there are issues with the slides. But the outline is start with the disclosure, but then I'll also talk a little bit about, give you a little context of what got me here in the first place. I'm not an engineer by background. I'm not an inventor, but how did we end up inventing the Nutrifone or the Fever phone, and then just give a brief summary. I'm a co-founder and a board member of the VitaMe Technologies. That's a disclosure. We have also been fortunate in getting a lot of competitive research grants from the National Science Foundation, National Institutes of Health, the International Food Policy Research Institute, Micronutrient Initiative, and Department of Defense. If you will indulge me for a couple of minutes, just to take a step back, my research program is mostly internationally based. We have field sites in India in a couple of places. We work in Ecuador. We also work in sub-Saharan Africa, primarily in Kenya right now in partnership with the University of Colorado. And so last year, Nature did a Twitter kind of a competition that summarize your research in 3 words, or summarize your, the kind of work that you do, or PhD thesis. And that set me thinking that what are the 3 words that define my research program? And as was mentioned in the introduction, I think identification, diagnosing, and intervening on modifiable risk factors, or identify, diagnose, intervene. That's kind of the summary of what my program is about. And when we as a tangent, what do I mean by modifiable risk factors? In this audience, I don't really need to stress upon it, but basically what I'm saying there is, or what the cartoon is saying is I need some medicine for an infection I'm going to get next week. And this is a question that a lot of people typically ask me very often, that what's an infectious disease physician like you doing in a field like this? And for me, these are very informative. So if you look at our colleagues at Institute of Health Metrics and Evaluation in Seattle put out these nice papers last year, both focusing on top 10 risk factors for mortality, one set focusing on the US, one set focusing internationally. And if you look at them and look at the top risk factors for death across the board, whether the US or outside, you'll see about 50% of the risk factors are related to nutrition. So that's my usual argument, that this is why I'm in the nutrition space. And so in practice, what we are trying to do is we are trying to set up large-scale surveillance programs so that we can pick up disease, pick up risk factors for disease or poor nutrition as early as possible. And those surveillance programs are catering to about 75,000 people across 10 villages in India and about 250,000 people in Ecuador. And so that's an identification piece. And the diagnosis piece there is that we want to diagnose both poor nutrition, and also risk factors for infection early on, excuse me, so that we can eventually intervene, both in the community setting as well as in clinical setting. The community setting, we do a lot of biofortification efficacy trials, both in urban slums of Mumbai right now among infants. And in the clinical setting, we work a lot among TB and HIV infected patients. So the whole reason for giving this background spiel is that most of this program, when I visualized it, and when we started setting up, the limiting roadblock was identification and diagnosis piece. So when we started setting this up, at our field site, we set up a lab, we got a nice, couple of autoanalyzers, we got a diasorin to do vitamin D, put us about $100,000, $150,000 in the red just to set up capacity with annual maintenance contracts, training our staff, and all that stuff to get maybe just the vitamin D assay up and running, let alone anything else. And so that made me think that this has to be done in a more cost-efficient way. Not only is the capacity limited, even when we set it up, it's really expensive. So, and that's not true just for the rural field site that we have in India. In Ithaca, at Cornell, of course, we can do all the nutritional biomarkers, but that's a research setting. If I have to go get my vitamin D tested, I go to a clinic in Ithaca, the sample gets shipped out to Mayo Clinic. And I will get, if I'm lucky, I'll get the results the next day, but typically it's about a week turnaround time. So when we're talking about comprehensive nutritional assessment, it's expensive, it's not available, and there are very few labs worldwide. For example, in sub-Saharan Africa or India, there are very few labs that can actually measure comprehensive set of micronutrients. So I started a partnership with faculty in engineering, David Erickson, and we started working together about 5 years ago now at Cornell. and he's an expert in nanofluidics or microfluidics, and we said that can we focus and can we bring some of these tests to the point of care? Can we give results in 10 or 15 minutes? Can we eliminate infrastructure costs? And so on and so forth. So that was our main challenge. The context, of course, was that there was a lot of talk about precision nutrition. There is a lot of talk about what to measure. So, for example, the biomarkers of nutrition and development set up in partnership across NIH, CDC, and WHO. They have been talking about and doing really, really good work around what are the things that we should measure. What defines a gold standard for, say, vitamin D status, or folate, or zinc, and so on. But there is very little talk around how to measure. When we talk about simple vitamin A assays, the WHO reports that only 1 in 5 pregnant women have actually access to a vitamin A assay worldwide. And they don't talk about affordability. They don't say that 1 in 5 actually gets it. They have access to it. And so there were a lot of issues around it, and similar issues in detection of infectious disease, which I won't really delve into today. So we started looking at what the point of care diagnostics that were available at that time, and majority of them are based on simple lateral flow assays, like a pregnancy test. And they are qualitative. They give you a yes or no answer. The quantitative one that's successful is the blood glucose one, but that's basically driven through the razors and blades model that the reader can be relatively cheap, but because once you have the person buy a reader, then they are buying it to your platform, and they'll keep buying those test strips basically for life. So that's where it commercially is successful. So we thought, why don't we use smartphones? And I'll come back to that in a second. And just to recap, our vision was, can we make something like the Square for personalized nutrition diagnostics? Can we, again, the same points, can we make it possible that it can be done with minimal infrastructure, with minimal cost, at the point of care, and the results can be available? And why we chose smartphones was because of all of these things that we can do. We can do location tagging, there is a camera, we can upload results to a server or send them by email or something like that. Most people know how to use it. We don't need to train people on it. And then most people already own it. So we don't need to invest in that infrastructure. So that was our solution. Of course, it was a pipe dream 5 years ago, but I'm happy to report that we have been able to make substantial progress on this. What we invented is what we call the Nutriphone. So you'll see the phone tag in pretty much everything that we have worked on. So there is an iron phone variant, there is a Zika phone variant, there is all kinds of phone variants. We are not very creative with names, I will say. But the idea again was that can we use a single finger strip, a single drop of blood from a finger stick? Can we apply it to the test strip? Take about 10 minutes for the test reaction, and can this be read at point of care with minimal training? So that was the basic idea. So now we have been able to develop these tests for vitamin D, vitamin B12, vitamin A, C-reactive protein, for ferritin, for iron status. And the idea is, just as a reference, the standard vitamin D procedure, you collect blood, you spin it down, take plasma or serum, use something like acetonitrile to separate out the D-binding protein from vitamin D, and then use some kind of fancy equipment, some autoanalyzer, to then get the output. What we did was we integrated all of this functionality on the test strip. And this is a simplified figure, but on the test strip itself, the blood filtration happens right there, the separation happens on the test strip, and then like any other competitive protein binding assay, there is competitive binding, and the intensity of the test line signal is inversely proportional to the amount of vitamin D in the sample. So this all happens in about 10 minutes. Similar results, we have seen we have published in scientific reports on vitamin B12 assay last year. This was one of our most challenging one from an engineering perspective, partly because the concentrations are so low. So we are talking about like 150 or 200 picograms per ml, and now we are talking about doing this measurement in 20 microliters or 40 microliters of blood. So the concentration was really, really low. So this was a huge challenge for us, and we were able to get really good sensitivity, like 100% sensitivity specificity around, or close to that, around the 300 picograms per ml. Below that, our percent error goes up to about 7% or so, which is if I might say so myself, not bad for a lab test. What we are now currently working on are things like ferritin, and can we multiplex them into one test? Can we do ferritin, say, C-reactive protein, vitamin A test like retinol binding protein on a single test strip? We just submitted a paper on this last week, and we have developed the prototype. Now we need to validate that in human samples. This is our vitamin D test. That's actually David. In the anonymous person up there is David getting tested, and you can look at, if you compare the accuracy to ELISA and stuff, we have a linear response when we compare it to ELISA. What we are doing now is just to make sure before submitting this paper, we are trying to compare it to LCMS and use the actual gold standard and see how well our results compare to that. Because every time we use an ELISA kit, the results also change, because as you know, the ELISA kits that are available on market, they themselves have a huge variability, about 20-25%. Other work that we have done is also on measuring total cholesterol. C-reactive protein actually is pretty final. The retinol binding protein work is going on. The D-binding protein is really preliminary. And we have a lot of publications. We just published another paper in Current Opinion in Biotechnology just last week, summarizing some of this work. And we are also doing field trials to figure out usability, as well as things like in India, for example, when the temperature goes up to 45, 46 degrees Celsius, it's 97% relative humidity. Do these test strips, what's the shelf life of these test strips? How well does the test perform in some of these settings? So we are doing a lot of this work there as well. We also just got an NIH R01 to expand some of this work to differential diagnosis of acute febrile illness. So can we diagnose if a child or an adult comes in with fever? Can we diagnose what the cause of fever is within 10 or 15 minutes? And the causes that we have listed here, that we listed in that are malaria, dengue, chikungunya, typhoid, Chagas, and leptospirosis. We are also expanding it to Zika based on all the global interest around it. So basically, just to recap, what we have invented is a mobile system or a mobile platform for doing comprehensive nutritional assessment as well as infectious disease assessment. We are calling it the NutriPhone and Fever Phone. But our aim really is bigger than that. What we want to do is that can one of these platforms, like a smartphone platform, be really the hub of the healthcare universe? Because what we are doing right now at the field sites, for example, is we are using iPads or iPhones to collect data. So you can collect all the data. We can do all kinds of location mapping. We can collect all kinds of sensor data. We can also do dietary assessment on these. And then we can have it as a mobile lab. So we can do all the results right there, which can then be used for diagnosis. It can be used for personalized feedback. It can also be used for triage or referral. I'm not going to talk about it, but we are also doing things like how can we use this to modify behavior. Particularly, that's mostly focused around adherence in clinical trials that we have going on. And this is being recognized in the press as well. Forgive the spellings up there. This is from Ecuador last year, the smartphone, but I like to joke about it because in Sanskrit or Hindi, smarth will mean capable. So I'm just saying that it's actually not a typo, it's a good thing. And they're recognizing it as that can the smartphone be our new medical specialist? I will not go so far as saying that, but I will at least say that it can definitely help us screen and get better care out to people in most resource-limited settings, and also in resource-rich settings to a certain extent. Okay. A lot of people to thank, particularly this partnership between David and I has been very fruitful over the last 5 years. As was mentioned in the introduction, we have set up a new institute at Cornell, the Institute for Nutritional Sciences, Global Health and Technology, with a vision of bringing or using modern technology to solve global health problems. And we have also started this company called VitaMe Technologies to bring this product to market. Lots of funders to thank. It's not possible without actual money, as we all recognize. And I will stop there, and thank you so much.
Outstanding.